Today we're going to see this fluid mechanics applications of finite elements and irrotational flow. As you can see, there are some restrictions about the kind of fluids that we can analyze with this. No friction between fluids and the surface, for example. No rotation or distortion of particles during motion. Examples of this application: flow of water through earth, flow of groundwater under dams and underground drains. So let me disappear from here, and then we'll go on. And the governing equation for a two-dimensional groundwater flow, as you can recognize in here, is pretty much like the application similar to the one we had for stress distribution, also for propagation of waves, magnetic fields, and now groundwater flow. So finite elements on the same kind of equation um, covers a lot of applications. In this particular case, you see that the case of x this one and kyy, this are the coefficients of permeability. It's similar in heat transfer. Remember, those coefficients were the thermal conductivities, right? We don't talk about conductivities, but we talk about permeabilities when we talk about this kind of fluid mechanics. And then piezometric head, which is pressure, measure, in this, on this measure. And then you have a recharge or pumping is Q. So there, the part where we have on the side here, you have the external loads in there. So let's go on. The boundary conditions for this, we have that the water will be moving through the region. You will be moving through the region, or it would be moving in the directly or at the angle. So that's in mathematics. In many equations, we use this so-called direction cosines, right? But this is the equation for the boundary conditions, So this equation, as I am making an emphasis, is the same as the torsion, same as the heat transfer, of course, without convection, right? The same format. You could say, it's not the same, but you could say same format like this. Okay, let's keep going here. If you have a situation where, if we have a situation where you have an example like this, for example, you have an aquifer here, where you have a stream. Do you see it in there? You have a stream in there. There's a we have a stream in there that it has a couple of pumps in there. You see in here, you have this on this side right here, and you have it also on this side over here. And so pump 2, and you have pump 1 over there. So we have a stream or a river, you may say, here. So here's what we have done on our ideal problem in here. You can see this is a regional aquifer, which means water distribution over some city or region that you want. So you have you have pressures here, you have pumps, you have the stream, and then of course this boundary that has been set up on both sides, that is impermeable boundary. So what to do? We implement this structure using the groundwater equations. Of course, we can have a simple program like fluid mechanics that like we have in our textbook, or in this case, we can use Patron software. How are we going to do this? We're going to treat this as a, we're going to treat this as, hold on for a second, let's see if I can get the cursor here that I want. This is the, we're going to treat this as a region where the finite elements are defined by using triangular elements or using quad elements or dividing here. Once you have that mesh, we should be able to make, hopefully make this pumps coincide with some nodes in such a way that you will be able to do this, put it like this. So you can see when you enter into the into any finite element software, you need the geometry, and what you're seeing in here is the geometry that we have. So we put the coordinate system, in this case global coordinate system, for the where the stream is and where all the other reference points are that allowed us to build the geometry. And of course is we need to do we need to do the impermeabilization on this side, impermeabilization on this side as well. This is it. We go and create a finite element mesh, which by now, if I ask you to do this on your own, you should be able to do it. In here, you will notice that not all finite elements are the same. You see, these are bigger than here. These ones are bigger than this. And perhaps around the aquifer, around the stream, which is going to be around like this, where the river is going to be, right? So you are going to have a different mesh depending on the precision you want, but you should be able to do this. So in this case, we are giving the several data, the seepage on the, and of course the length of the river, and we are going to allocate the nodes for the seepage to the along the river, to see how much water goes away. So what is important to remember is that the pump doesn't have to coincide with a node. So if you have a situation like this, for example, you have a finite element in here, and you have the pump right there, yeah? And here we're using the equations for section 8.6, and then and you remember that page 57 of the textbook to obtain the values of these constants. And of course, we define the shape functions for this, and then of course the values of the pump. Once we have this, we will calculate the nodal values and put actually the elements. These are the nodal values on the elements in there. So the element matrices that we use, this come from our simplification of the equations that happened in chapter 7, you recall. And these B's and C's are again from page 57, two-dimensional finite elements. So in the end, the load you have the for the for the pumping recharge, you have for the seepage, which would be a negative in and out of the element, and the seepage in and out of the element using this, and then this would be the seepage in and out of the element using the different sides. So you could have a seepage on this side and not on this one, but you could have it on this side. So this will consider all of them. This is what will happen if you do a computer simulation. If you do a computer simulation using Patron or other software, these are the contour lines that you will see. Do you recall how finite elements create these contour lines? Okay, just in case, let me just remind you. Um, let me show you here. Do you see this? This is a line right there that touches this point and touches that point on this element, see? And if you have this other finite element in here, the intersection is here and the other is over here, see? I want to call your attention to this. Observe this and this one. Observe this one like that. Like that, all these points. The computer has to figure out to create this line. But do you notice one thing that is common to all of the points that I just highlighted? Every single line crosses 2 points on a finite element. And you know for a fact that 2 points define a line, right? So if you see a nice curved fringe that you see of values in here, and this nice fringe that you see of values, like this, it's not a line that was drawn just nicely as a contour line. Think about this. Every single little piece of the line is made of 2 finite elements. I'll highlight it again for you. Look at this one. I'm going to do it bigger. See in there? Every point that I am drawing intersects 2 sides of the finite element, of each finite element that goes through. So even this one that looks straight has gone through 4 elements. And this is how computers design those nice colors that display, I should say, those nice colors we see in finite element modeling. And of course, each one of these is going to be one level of the head in there, the solution. And that's how we solve the finite element problem here. And in here, if you locate the pumps now, you notice this contour is not the same as this one. So it depends how you define the source in this case. The pump becomes the source in here, see? Right there. No? Now this is the logic of if you want to make your own program, but I am not encouraging that. But in case you want to, this is how you could do it. So we're not gonna dwell too much into that. But rather, it's sufficient to say is that this is the This is the how we do groundwater flow. I think next we'll examine how fluids move on pipes.